Hello, everybody. I don't know who decides that we should be dark.
Put a bug in your coffee, April Fools.
It's the same people who prefer permanent daylight savings time. Want it to be dark in the morning. Pox on all your houses. Anyway, very good. All right. So, right. April Fools. No, this is actually what's listed for our exam. No, we're not going to have a final exam starting at 7:30 in the morning. That's ridiculous. So we will have to just figure out when to have it, depending. So I will ask for your schedules. Some people said they would like to get it done as early as possible, get it over with. And yeah.
Those two Maxwell equations.
We'll get to that. We'll get to that. One thing at a time. One thing at a time. I'm talking about this now. We'll get to that in a moment. So what I'd like to do is I'll send you a little survey about when you're having your finals in other classes, so that won't conflict with that. Okay. The other thing I wanted to talk about was the upcoming midterm exam, which will be on April 15th in class. This is what it covers. So it covers magnetostatics and quasi-statics and electromagnetic waves, as we're discussing through today's lecture and through the problem set that's due on Thursday, okay? And next week, on Thursday the 10th, I believe, we'll have a review session in class, okay? So we'll come prepared with questions, what is you want to have some review on, okay? All right, now let's get to it. All right, so last time we talked about Maxwell, so-called macroscopic Maxwell's equations, okay? So this is the way we describe electromagnetic phenomena at the macroscopic scale when we're thinking about electromagnetics in materials. A material could be a gas, it could be a liquid, it could be a solid, it could be a plasma, which is an ionized gas. And we kind of coarse-grained our description and thought about the macroscopic sources that we broke up into two components. So components which involve freely flowing current and unbound charges, free charges, as well as the charges and currents that are bound up in materials, okay, whether it's in molecules, atoms, solids, etc. And to good approximation, we can think about that bound charge for a neutral material as dominated by the electric dipole moments associated with that material, okay, because it has no monopole moment. The monopole moments, we kind of, whatever's unbound with ions that are flowing around, we would put that into the free component. And that bound charge density is related to the density of electric dipoles, which is called the polarization for some reason, as minus del dot G. And the bound current has two components. There can be oscillating charges, oscillating dipoles, that's a dominant effect, and that oscillating dipole gives rise to a current density. And if there are magnetic dipoles in the material, then that gives rise also to a contribution. Yeah, Colton, you had a question? No, okay, I thought, maybe I misunderstood, excuse me.
Well, the top left or right Maxwell's equation, del cross B equals 1 over C d dt.
Yes.
Wouldn't it be the other way around? Del cross E?
Yeah, absolutely. Thank you. That's the, this is, pardon me, this is Faraday's law. That's, right. So these are the macroscopic Maxwell's equations, now hopefully written correctly. And they involve these new fields, D and H, which in some sense are combinations of the fields that we have expressed before and contributions from the bound dipoles in the material, okay? So D is called the displacement, and H is sometimes called the magnetic field. It's the auxiliary magnetic field, okay? So these are the macroscopic Maxwell's equations. And we also discussed briefly at the end of lecture last time that we can think about material response. So if there's some material and there's some local electric field at some position, there can be, you might try to align the dipoles along the direction and polarize the sample. That's why it's called the polarization, because you're polarizing the sample. If it's an oscillating field, then you get oscillating dipoles, okay? And so the amount of induced dipoles will depend on the strength of the field. Now, if the field is sufficiently weak compared to the fields that bind the charges together, such as an atom, the electron is bound to the nucleus, and it's a pretty strong field that binds the charge, then typically speaking, that for, weak fields, and that doesn't mean too weak at the end of the day, but it means is weak compared to the strength of the fields that are internally binding the nuclei to electrons, which is a very strong field, okay? Then if that's the case, then you'll have what we call linear response. Okay? Because generally speaking, if you have something bound together, there's some potential that describes that binding, and if you're displaced very slightly from equilibrium, it'll look like a harmonic oscillator, okay? That's true for any binding potential. So under that case, we can say, oh, the induced dipole, well, it's going to depend if this thing is oscillating at some frequency omega. Let's say if we had an oscillating field oscillating at frequency, then the induced dipole will depend on the frequency typically, especially if that frequency is near a resonance. Then you'll have a very strong response, will be highly frequency dependent, right? Because if I'm right near the binding resonance, it's going to be very different than if I'm away from resonance. So generally speaking, we would say that the polarization density at a certain frequency is, if we have a linear response, is proportional to the field that's present, okay? Now, it's also the case that in principle, this could also have some spatial dependence. If I have a crystalline structure, and it could be that different spatial directions respond differently, but to the degree to which I have a homogeneous material, I will ignore the position dependence. This is chi, not x, okay? And this we call the electric susceptibility. So the susceptibility is how susceptible the thing is to becoming polarized, okay? And if for this kind of linear response, this is sometimes called chi1 as opposed to chi2 if I had a quadratic response, or a chi3 if I had a third order response, that's called nonlinear optics. This is linear optics. Yeah.
So we can kind of, that chi includes all of them right now, the way we have it at the moment, that includes all responses, linear and chi.
No, this is by definition linear
This is the linear
response. Otherwise, I would have this, I could call this chi1, and I might have a chi2 that, you know, will have two indices.
Okay.
So, and then I'll have a chi3 and chi4. And the nonlinear response is, as again, what's happening is I have some charges bound to the material, and I'm stretching them by, say, applying a field to them, a light field, maybe it's a laser beam. And the question is, how far do I stretch it? If I stretch it not very far from equilibrium, it's like a harmonic oscillator, and then it's well approximated by this.
Okay, and so if I'm being like pedantic.
Yes.
Is that,
Really?
should that equal sign be an approximate? In this case,
Yeah,
like
no,
in
I mean,
theory?
it's a semantic thing. If I'm calling it linear response, and that's the definition,
I see,
okay? Yeah,
So the quadratic would have two indices, so is the power the rank of our tensor? So linear is.
yeah, it's, well, yeah, exactly, yeah.
And so
It's
two would
how
be
many,
rank three.
it would be rank 3. So this is a rank 2, this is rank 2, and then I have a rank 3, rank 4. It depends. Again, the tensor nature of the response kind of depends on the nature of the material. Okay?
So how many indices are there, Jerry?
Here there are 2, because this is a tensor. But let's not get into nonlinear optics. We have enough to understand at the moment, and let's get through this, okay? So this is just the linear response. And then B, we said was E plus 4 pi times P would have this form for the linear response in linear optics. And this combination is called epsilon. Okay? And epsilon is the permittivity. Okay? Now, if I have a isotropic material, then epsilon is a scalar. It's not really, it's isotropic in terms of the isotropic, I should say, response. So meaning that it's the same response whether I'm pushing it in this direction or whether I'm pushing it in that direction, it responds the same way. Yeah.
So, if it's isotropic, that consequently means the susceptibility is a constant.
That's correct.
Okay.
So if that's true, chi, epsilon, and chi is also a scalar, absolutely. Okay, so in that case, we rewrite epsilon as 1 plus 4 pi chi. Generally, this is some function of frequency, and as we will see, generally a complex number. Yeah.
Can you have a non-linear isotropic response?
Sure. Absolutely. So the ratio of this to epsilon naught, which is the permittivity of free space, is called the dielectric constant. And CGS, epsilon naught is 1. So the relative permittivity is also called the dielectric constant. A dielectric is another name for an insulator. Okay, where all the charges are bound. Okay? All right, very good. We can also have a magnetic response, and as we said, we typically define that relative to H, because H is the thing that we typically control in the lab by the free currents we apply through wires, and there can be some magnetic dipoles induced, and so the induced H is the magnetic susceptibility, the induced magnetization, pardon me, is defined this way. Okay. And as we can see over here, B is equal to so we can write this over here in H plus 4 pi times the magnetization then this is equal to 1 plus 4 pi times pi magnetization dotted into H. And this we call the magnetic permeability. Now, again, in CGS units, these things are dimensionless. In SI units, they have dimensions that allow us to translate between charges and currents and fields, but we, on lecture 1, made a particular choice in those constants. Yeah, Don?
For a conductor, would permittivity be 0?
We'll get to conductors in a minute. Let's hold off for a moment. All right, so very good. So again, if I wanted to think about the say what the displacement is as a function of time, I would generally have to superpose what this is over all frequencies. I would take the inverse Fourier transform. Right? So, I'm sorry, this is, I would add up all the guys with this, each one of these has this frequency, okay? And so if we put in, for example, the case of having linear response, it looks like that.
So, if we're writing down the Fourier transform, why are they both function of x on both sides? Shouldn't one be in case
It's
space?
a Fourier transform in frequency and time.
Oh.
It's at a fixed
Oh, I
position. So this is, basically all we're doing is superposing all of the fields to get what it is in the time domain, okay?
I was looking at the wrong variable.
Yeah, it's quite all right, no worries. So this is a Fourier transform with respect to time, all right? This is the frequency domain, this is the time domain. X is just a fixed, we're looking at some position in space. So if we look at this Fourier transform, it's a Fourier transform of a product of things, and you know that the Fourier transform or inverse Fourier transform of a product of functions is a convolution, right? So this is which would generally be a tensor dotted into the electric field at that position integrated over T prime, okay? So what this says, generally speaking, is that the displacement at some time is not instantaneously related to what the electric field is at that time, but there can be a delay, okay? This is what we call the response function. Now, if this function is some number times a delta function, then we would say this is instantaneous response. That is, what the polarization is at a given time is instantly related and it responds instantly fast, okay? So if that's the case, let me ask you the following question. If I had this kind of response, where this is just some constant scale, it's constant tensor, independent of time. If this were the case, what would it tell me about the frequency dependence of the Fourier transform? That's to say, what does this function look like in the time?
It's also a constant.
It would be independent of frequency. It would be flat, right? So if I have a flat frequency response, that would say that psi tilde of omega is a constant. Because something which is flat in frequency space is a delta function in the inverse space, right? And so to the degree to which, to some approximate degree to which the susceptibility is the same over all frequencies is a degree to which this is a good approximation.
Okay, I think it makes sense.
So like and we'll talk, I mean, again, if I have a bound charge, and we'll talk about this in next lecture on Thursday, thinking about it as a bound charge, as a harmonic oscillator, if I'm driving the system close to that resonance, it's going to have a very strong frequency dependence. This is going to be a terrible approximation. But if I'm detuned very far, detuned means tune away from resonance, then I'm going to have a very flat frequency response. And so away from resonance, I can think about a piece of glass as being pretty pretty instantaneous response. Okay? All right, very good. So, excellent. Yeah, no.
Over there where we have a d time domain, is that equal to the inverse Fourier transform of the frequency domain d?
Oh, geez. First of all, this should be P, because P is proportional.
Okay. Should the p on the left-hand side also have a squiggle?
No, this is the real
Okay.
real polarization, which is proportional And it's the Fourier transform. The Fourier transform will be complex, but this is real. I could have put epsilon, but this is chi. Okay. Yeah.
A delta function gets Fourier transformed on the sine.
No, if I have a sine or a cosine, I'll have two delta functions, one at e to the plus I omega t, one at e minus I omega t. But as you may remember from wave mechanics, a position eigenstate is something which is a superposition of all momentum, right? So a delta function in one domain, the Fourier transform is something that's completely flat. Very good.
Who bought this?
Very good. All right, so let's now talk about, and we're going to look at, consider Maxwell's equations for linear response that is instantaneous, which is also known as dispersionless. We'll remind ourselves about dispersion in a little while. Dielectric / magnetic materials. We'll come back to conductors in a moment, all right? So in that case, I'm just going to write D at a position and time is instantaneously related to the electric field. So now this is correct because this is D, not P. And we have that B is equal to mu times H.
Is both linearity and instantaneous required for it to be dispersionless?
No, it's just the instantaneous part just means it's independent of frequency.
Okay.
I could have a nonlinear response as well. That's okay. And I'm also going to think about it as, in addition to be lossless, I'll explain what that means in a moment, so that epsilon and mu are real. Okay. So when that's the case, we can look back at our equations for Maxwell's equations, and we have that del dot E is equal to 4 pi rho free over epsilon. Del dot B is 0. Del cross B is equal to minus 1 over C dB dt. And we have del cross B is equal to the H, so that we have 4 pi over C mu times J free plus mu times epsilon over C dB. Okay? Substituting these guys into Maxwell's equations. So this is, these are Maxwell's equations under this condition, these conditions here. And let's suppose, so now we're in a dielectric. So in a dielectric, there's no free charge and there's no free current. Okay. And so now what I want to do is solve these equations. All right? And we can do it the same way we did in vacuum. When we had vacuum, we also had no charges or currents at all. The only way that this whole thing is modified by the fact that there's bound charges and bound magnetic dipoles is through the permittivity and the permeability, right? That's the only change. And the way we solve this equation was to decouple them to get the wave equation. So how do I get the wave equation from Maxwell's equations?
Curl.
I curl. I'm gonna do my curls. All right, so I take the curl of the curl. And using the old back minus cab rule for derivatives, this is equal to the gradient of the divergence of E minus the Laplacian of the E, which is equal to minus 1 over C d by dt of the curl of B, which is equal to minus mu times epsilon over C squared dE. Okay? And so, when we put that all together, what we see is that del squared minus mu times epsilon over C squared of E is equal to 0. Oh, sorry, that's not equal to 0. Times d by dt squared of E t is equal to 0. Okay, and it's also true for B. If we would do the curl of the Ampere law, we would get the same equation. So what we see is in this kind of material, the electromagnetic field satisfies the wave equation. Okay. And what's changed? Well, now we have this mu and epsilon. And so what this tells us is that the phase velocity of a plane wave is what? In this kind of material, just looking at the wave equation.
C over root mu epsilon.
C over root mu epsilon. Right? Because this is equal to 1 over the phase velocity squared. Right? So the wave equation in general in 3D this is the phase velocity.
You said that in this material, our fields satisfy the wave equations. Can we have materials where they don't?
No, they satisfy a modified version of the wave equation. We'll see. They satisfy some wave equation, but it satisfies this particular wave equation of this form.
Of this form having the mu and epsilon, or just the 1 over VP squared?
No, well, let's look at, we'll see an example in a moment. Let's hold on. Someone else? No, good question, just scratching. All right. Very good. All right, so now I'm interested in, when I think of a plane wave, so there are plane wave solutions to this. For example, I can look at the electric field of this guy, and I can look at plane wave solutions by thinking about putting in this ansatz, okay? Where this is a general amplitude, generally polarized, it might be linearly polarized, it might be circularly polarized, right? And so if I take this and plug it into the wave equation that we derived from Maxwell's equations, we can get a dispersion relation. The dispersion relation tells us the relationship between omega and k. So if I plug this in, the del becomes a minus an I dot ik dot ik, which is minus k squared, minus mu epsilon over c squared times minus omega squared times E0 equals 0. And since that's to be true at every position at every time, it must be true that this coefficient in front is 0, which means that omega is equal to let's see, I want to say this, V phase times K, right? Everyone see that? Let me maybe write it in fewer steps. This says omega squared is equal to c squared over mu epsilon times k squared, which says that omega is equal to c over the square root of mu times epsilon times k, which is the phase velocity, right? So the phase velocity is always equal to omega over k, or a plane wave. We can see that because if we rewrite this guy as e to the minus I omega t minus we have this is equal to the retarded time, right? I can write this as, let me write it this way. This is equal to, yes, divided by omega over k. If I multiply this by omega, I get back this expression. And what this is saying is that what I see at my position at some time t is what the wave was doing at a retarded time, having moved backwards by this phase velocity. So the phase of the wave is moving at this velocity. And that phase velocity is equal to c divided by the square root of mu times epsilon, which means that the phase moves generally at a speed that's slower than the speed of light. Generally, because actually you can have the phase velocity be greater than the speed of light. Really? Yeah.
When you say generally, do you just mean like mathematically, or do you mean like physically?
Physically, there can be media, there can be situations where the phase velocity can be greater than the speed of light.
Whether it's like a wave, but the group velocity.
That's right.
Yeah.
We'll come back to that. Yeah. Okay, now, what this says, of course, also is that, so the wavelength inside the material just from this definition is periodic with a period lambda, which is always 2 pi over k. Okay? And k, we just said over here, was equal to omega over the phase velocity. Okay? So this is equal to, if I think about this as the 2 pi over omega is the period, which is 1 over the period frequency, where mu is equal to omega over 2 pi. So what this tells me is that where the phase velocity is equal to c over, oh, I should have said, by the way, that this is the index of refraction. N. Okay? So, what we have here is that this is equal to C over nu divided by the index of refraction. Okay? So, in vacuum, what is the index of refraction?
1.
1. Because mu and epsilon are 1. Generally, this will be bigger than 1. So in vacuum, this is 1, and I can also write it the other way. C over, what's nu? C over lambda. That's in vacuum. But in the medium, the wavelength will be generally smaller than the wavelength in vacuum.
It's going so
Okay.
much, so it's compressed.
Exactly. So as Benny was saying, if I have some material, okay, so here's the wavelength in vacuum. Okay. And now what I have inside the medium Now, this is something I want to emphasize. The frequency is the same in both, here the frequency is nu, and this is inside the dielectric, the frequency is also nu. But the wavelength is different. Why is that? Well, as Benny was just telling us. There's just something bobbing up and down over here, like an antenna, that is causing something to radiate. And the radiation comes to me, and I see the electric field going up and down at the frequency of the signal. That same signal will get to me, and the frequency of the signal, I will see it locally at my position, oscillating at the same frequency as the source. But because it's moving more slowly, because the phase velocity was assuming this is bigger than 1, is less than the speed of light, it's moving more slowly. And so in order for it to go up and down at the same rate, it has to bunch up. Okay? Yeah.
I was gonna say, if it wasn't moving up and down the same rate, we'd have discontinuity at that boundary, right?
We would. But more importantly, it's just causality. There's a signal that I'm seeing a certain signal. The signal is coming to me, it's propagating. The signal isn't changing. What's changing is how it's propagating. Okay. Very good. What about the magnetic field in this problem? So, given this electric field, what is the magnetic field, and how would we find it? We'd use Maxwell's equations, right? So, if we use the Faraday law, this tells me that del cross B is equal to I K cross B. For this, let's put this in our, we're going to take the real part in the end. Is equal to minus I, or minus 1 over C times minus I omega B0. Okay. So this tells me that if I have a magnetic field, well, if I have a plane wave, then the amplitude of the magnetic field is related to the amplitude of the electric field by K times C over omega cross E naught. Okay? And what is this? You have to be a little bit careful because we're not in a medium anymore. I mean, we're not in vacuum anymore, we're in a medium, so we have a relationship that's a dispersion relation over here, which says that omega over c is equal to k times k over the index of refraction. Okay? So, with that said, this is saying that this is equal to the index of refraction in vacuum, n is 1, and we just said that B0 was crossed, but this E and D do not have the same magnitude in a medium, okay? So, they don't have the same amplitude anymore. Very good. Yes. You have a question?
Yeah, is that the case for all reference frames? There does not exist a reference frame where E and B are the same in the medium?
Good question. Let me think about that. I think the answer is yes, but let me think about that. Come back to you next time. Think about it harder. I think the answer is yes. There is no frame where there is. All right. So what about energy in the fields? So remind ourselves that in vacuum, we have that the electric field energy density is that. The magnetic field energy density is that. We have the Poynting vector. And we have Poynting's theorem, or the continuity equation, for energy flow, which says that the rate of change of the local energy density is related to the flow of energy and how much energy is either absorbed or created by the sources. Okay, we all remember that. Or if not, all right. So now let's talk about it in the dielectric. Yeah.
Is it conventional to write the divergence of S on the left-hand side of the time derivative instead of just equating the time derivative to everything on the right-hand side?
I have no answer. It's probably the first time you've ever heard me say that, but. I think part of the reason is that we think about this as, this is sometimes known as the, there's a name for this kind of derivative, where you have both the part that's moving and the time derivative. What's it called?
Convection derivative?
What, say again?
Convection.
Yeah, convection or something like
I
that.
have a question about
Yeah,
that.
yeah.
It's a long question.
Okay. All right, so let's anyway. All right, so that's just how we write it. All right, so what we know is this is the following. It's always true. So minus J dot E, by no matter whether I'm in the material or not, is equal to the rate at which energy is created in the electromagnetic field. This just comes from Lorentz force law, which is true whether I'm a material or not. That's that, okay? Now, from the macroscopic Maxwell equation, we have J. J we can find from the Ampere Maxwell law. So we have that del cross H is equal to 4 pi J, this is the free current, plus 1 over C dD dt, which tells me that J free is equal to C over 4 pi times del cross H minus 1 over 4 pi dD dt. So I can plug that in and I get that minus J free dot E is equal to minus C over 4 pi E dot the curl of H plus 1 over 4 pi the electric field dotted into the partial of D with respect to T. Okay? So now I can think about, as we did the other lecture, taking this derivative and thinking about the product rule with curls. Okay, so the divergence of E cross H using our favorite buddy, the Einstein summation convention, is the part respect to I with the ith component of this summed over I. And the ith component of that is epsilon I jk ej hk. And the derivative comes through that number, and I get epsilon I jk partial I partial j h sub k plus epsilon I jk. This epsilon has nothing to do with the dielectric constant. Ej partial I hk. All right? And so what is this? Well, this is equal to, if I put the k, this is the curl of E, its kth component. Right? Everyone with me? Doing the secret permutation. And what is this guy? Well, I have I and k, I have to flip them, so it's a minus sign. So this is equal to Ej times minus curl of H. Okay. So this is equal to H dotted into the curl of E minus E dotted into the curl of H. Okay? So what this tells me, and the curl of E is equal to minus 1 over C dB dt. Okay, using Faraday's law. So now we can plug in over there, minus E, this is equal to, so that tells me that minus J free dotted into the electric field is equal to the divergence, or C over 4 pi, times the divergence of E cross H, plus 1 over 4 pi E dotted into dB dt plus H dotted into dB dt.
Excuse me, sir. You
Yes.
are making use of D here. Does the D, like, is the displacement or the polarization? Because you change.
No, excuse me for that confusion. D is the displacement, and D is equal to always E plus 4 pi P, by definition, and this is D. And D is what appears in the Maxwell equation, not P. I'm sorry for my earlier confusion about P and D, but this is a definition. P is chi E, and D is epsilon E. Yes, sorry for that confusion earlier. All right, so this is Poynting's theorem in matter, okay? In this kind of, so this is Poynting's theorem in matter. Okay, I didn't make any real distinction about linear or not. I just used the macroscopic Maxwell's equations at this point. That's all I use. I didn't say anything. I didn't use these here at all. So there was no linear response. There was no instantaneous response. Nothing. Now I'm going to make that assumption about the nature of material. So if I have a linear dispersionless then we just said that D is epsilon E. Okay? And we'll also say that B is mu times H. Okay. So, what that tells me then is the following, that under those assumptions, we have the following. D by dt of epsilon over 8 pi e squared plus 1 over 8 pi mu b squared plus the divergence of S is minus J free dot E, where S is the Poynting vector is equal to E cross H times C over 4 pi, which for a linear medium is equal to C over 4 pi mu So, what we see here is in a dielectric, the energy density in the fields is modified by mu and epsilon in this way, okay? You have epsilon E squared and 1 over mu B squared. We can also write this, as we sometimes do, as mu over 8 pi H squared, because B is equal to mu times H. So B squared as a mu squared, and this looks a little bit more parallel, okay? Very good. So, it's actually useful to sometimes think about, for a plane wave, if I have a monochromatic field, we say in this expression here, we have that the magnitude of D was equal to the magnitude of E times the index of refraction. The magnitude of H is B over mu, and B over mu is N over mu times D, but N is equal to the square root of mu times epsilon, which is the square root of epsilon mu times D, which we sometimes write as this, where Z, defined as mu over epsilon, is known as the wave impedance. So the impedance is something that is known well to electrical engineers or people who work with electronics, is a kind of form of resistance. When we think about resistance as the ratio of voltage to current, okay? V equals IR. And so I can think about the impedance here as the ratio of the electric field over the magnetic field, where I think about this related to the voltage and this related to the current. In MKS units, E has the units of volts per meter, and H has units of amps per meter, which means that this is volts per amp, which is ohms. Here is a dimensionless quantity. Okay? Yeah,
So here we got a real value. In general, can we get complex?
absolutely. And that's because, and we'll do that on Thursday. For the moment, we're just dealing with this case. Okay? So let's look at, for a plane wave, how much energy is stored in the electric field and how much energy is stored in the magnetic field. So, for a plane wave, we have E is equal to E naught e to the I k dot x minus omega t, and the energy density in the plane wave time averaged is equal to 1/2 E start at E, divided times epsilon over 4 pi. So this is equal to epsilon over 16 pi, the amplitude squared. Okay, so that's the time average energy in the electric field. In the magnetic field, we have 1 over 8 pi mu, a half B star B, which is 1 over 16 pi mu B naught squared. Okay. But B naught is the index of refraction squared, 16 pi mu B naught squared, because we said that B naught was equal to the index of refraction times E naught. And the index of refraction is equal to, or index of refraction squared is what? Mu times epsilon. And so this is equal to epsilon over 16 pi E naught squared. Okay, which is equal to the, so the amount of energy stored in the electric and magnetic field is the same. Okay, that is what's true in these units. Yeah.
Even though the magnitude in the medium is different.
Right, because of the way,
Because of
the way the energies are stored.
Because of the mu
And the epsilon.
and the epsilon.
Yeah. What about the flow of energy? Let's look at the intensity of the field. The intensity is given by the expected, or the time average value of S, right? And that's equal to, for this is the time average value of C over 4 pi E cross H. And for this monochromatic field, this plane wave, that is then equal to the C over 4 pi times a half the real part of E0 star cross H. That's how you take a time average if you have a monochromatic oscillation. It's 1/2 the product of that times the star. Or the other way around. Now, H, we said was, or we can write H as E over the wave impedance, okay? So this is equal to C over 8 pi. This is the magnitude, the cross product is in the direction, so this is equal to E0 squared over the wave impedance in the direction of propagation. E cross H is the magnitude of this times the magnitude of that times the direction of the cross product, which is that.
What happened to the tilde after here?
Oh, it's in there.
Oh, okay.
It's all about context. Yeah. And the wave impedance was the square root of mu over epsilon, so this is equal to the square root of epsilon over mu times, I forgot the factor of 2 there, so there's an 8 pi over there. E squared in the direction of propagation. Okay? And let me multiply this by epsilon and divide by epsilon. What? I substituted in that Z was equal to mu over epsilon, and I took a 1 over, it became a root epsilon over mu. And so what we find then is that the S over here is equal to C times divided by the square root of mu times epsilon times epsilon over 8 pi E0 squared in the direction of propagation. This is the phase velocity. This is the total energy. The sum of the electric and magnetic energies added together gives us this. And so what we have is that the intensity of the field is equal to the energy density flowing at the phase velocity in the direction of propagation, as expected.
You have an epsilon over epsilon, just to.
I did. I multiplied top and bottom by 1.
Okay.
Or I multiplied by 1 by, so that I can rewrite it in this form. So the important point here is that in a plane wave, we think about which of course is infinite, and so we can't actually have a plane wave, but the energy density is flowing here at the phase velocity, and that's the total energy density.
Whereas in different mediums, well, we would just change our mu and epsilon.
We would. So we're going to talk next time about the case where we have dispersion and loss. Let's just go yeah. Did you have a question, Tristan?
So I know that the phase velocity can be faster than the speed of light.
Yeah.
That's always explained away as, oh, it is, but it's not transferring any information, and so it can be. Will this equation ever work in a situation where your phase velocity is faster than light? Okay.
Yeah. The energy, and what's even more crazy, and something you probably didn't learn, is that the group velocity can be faster than the speed of light. And it also can be negative. It can go backwards in time. Wow, we'll get there. That'll be an extra credit homework.
Can it be imaginary?
Well, yeah, there are. All right, let's now consider the case of a conductor. So let's say we have some conductivity, sigma. Now, as you're studying in your homework, generally the conductivity will depend on frequency, but let's think about this in the case that we have something like a radio wave that's a low frequency, and this is like the static conductivity, okay? And so we'll just say J is equal to sigma E. Generally, this is complex, it depends on the frequency, okay? So if we look at del dot J, that's equal to that. And if we have this kind of dispersionless material, then del dot E is rho free divided by epsilon, according to the modified version of Gauss's law. But del dot J is equal to minus d rho free dt by the continuity equation. This is my free current in the conductor. So we have an interesting equation here which says that inside the conductor, the free charge density as a function of time is equal to whatever it was at the initial time, e to the minus solving this differential equation. Which means that as this field propagates in, the amount of free charge density is going to exponentially decay very rapidly depending on the conductivity. So this goes to 0 in a time T that's sufficiently big compared to epsilon over 4 pi times 1 over the conductivity. And then we all remember that in CDS, the conductivity has the units of a rate, because it's related to the rate of collisions in the material. So this is the case. Yeah.
If the free charge density is going away, then where's the free charge going?
It's not that there's no free charge, it's that the free charge density, the amount of positive versus negative, in the same way that if I have a conductor and I have current flowing in it, and it's a constant current, the electrons are moving over the ions in such a way they don't bunch up relative to the ions. They spread out so that the charge density is 0, but there's still current. It's just that that you can't get the charge bunching up anywhere.
But as time goes on, the density gets smaller and smaller and
So
smaller.
that means that there's an equal amount of density of positive and negative.
Okay, sure.
That's what it means. So the current is not necessarily 0, because the current is proportional to the electric field, but the charge density is 0. In the same way that when I have constant flow of charge in a magnetostatic, I have current, but I don't have a relative imbalance of positive and negative charge. Yeah.
What if it's a charged conductor?
If it's what?
It's a charged conductor, let's say there's an imbalance.
Yeah, I mean, well, then I don't have this constitutive relation. Okay, this is for a neutral conductor. So I just want to quickly write down what do Maxwell's equations look like in this case. So let's come back, let's see if we have it somewhere. Yes, we do. So this thing becomes epsilon E. Okay? So let's now write down the wave equation, including the conductor. So I have del cross E is equal to minus 1 over C dV dt, which tells me that del cross E is equal to minus 1 del dot E minus del squared E is equal to minus 1 over C, and B is equal to mu times H, so that's d by dt del cross H. Writing D is equal to mu times H. But del cross H is written over there somewhere, and that gives me this thing is equal to minus 4 pi mu times sigma over C squared d by dt of E minus mu epsilon over C squared, and H is equal to this. What we just said, if rho free goes to 0, we can neglect that inside the conductor, and we have the following equation. Del squared plus 4 pi mu sigma over C squared d by dt minus mu epsilon over C squared d by dt squared E equals 0. Notice, this is not the same wave equation that we had in the dielectric. We have this extra term over here.
Due to being conductor.
this is the conductivity. The conductivity were zero, if this were a pure dielectric, this term would not exist. And we had the wave equation. This is a modified version of the wave equation.
It's strictly more general.
It has this first derivative in it. And we're gonna see what that first derivative is. It's kind of like a damping term. If you think about a harmonic oscillator, you have a second order derivative that is related to, you know, the restoring force, which energy flows back and forth between kinetic and potential energy. In this case, it's between electric and magnetic energy, that's energy flowing back. This is ultimately related to the fact that we can absorb energy due to the conductor, and that energy is going where? Into heat. And it's going into heat because we have a finite conductivity because of collisions. And those collisions that the electrons are having in the material causes energy to be lost, and that loss of energy in the field is going into heat in the material. Yeah.
So for a perfect insulator, that clearly goes to zero, right?
Yeah.
What about a perfect conductor?
For superconductor, well, that's more complicated. There's much more complicated stuff because of the whole way in which the Magnus effect and the way that Faraday's law is affected. But we can think about a very strong conductor. The other thing, what we're studying, we meaning the royal we, including you, are studying in your homework, Farouk, I'll get you in one moment, is, so here I treated the conductivity as a constant, as a number. In general, as you're studying, if you haven't already done the problem, the conductivity itself will depend on frequency, because the way in which you have collisions versus the fact that it's being shaken back and forth by the field affects the response. So generally, the conductivity is frequency dependent, and we have to think about this equation. And so the way in which a material is conducting depends very much on the frequency. If I have X-ray vision, I can see through metal because at those high frequencies, the conductivity is very low. And the electric field can penetrate the metal. Whereas if it were microwaves or something like that, it's a very high conductivity. So generally speaking, all of the material response, whether it is the bound charges or the free charges, are going to be frequency dependent. Farouk.
Concerning the difference between the rho dt, you know, in magnetostatic we claim that for a steady state, the rho dt is always zero. So I don't know why are we having the rho dt of free to be existing here?
So this is the equation of motion that tells me about conservation of charge. So the equation of conservation of charge tells us that the rho dt is equal to minus del dot j. But for the specific case we're looking at, the current is related to the field in this way. And the field is related to the charge density in that way. And these things together give us this constraint. These two things together with conservation of charge tells us that in a conductor, I can't bunch up positive versus negative charges. They have to equilibrate in a way such that, and it happens at a very rapid time scale. So I can ignore any clumping up of charges and just think about the flow of charges. Yes, Donald, but we have to get out of here soon, but I'll
Can conductivity be complex?
What's that?
Can conductivity be complex?
Absolutely. It will be. You do the homework, you will see that. So the connectivity will be complex. And generally speaking, yeah, so let's call it quits. Have a good rest of your day, everyone.
Very dense. Question.
Yeah.
Is row 3 of 0